Welcome to the Taieri field trip. We are here at our first stop at the Taieri Lookout, and today we have two main goals for this field trip. The first goal is that we're going to look at the geomorphology of the Taieri region and relate it back to the tectonic history of this area. Our second goal is to learn something about fluvial processes. So we're going to be going down to the Taieri River and making some measurements and observations at a few different areas along this river to compare how the river changes from the upstream through the downstream. Here at the Taieri Lookout, the reason that we've come here is because we get a really nice overview of the landscape here and the geomorphology, so the landscape features. The first thing that you'll notice is down here in Mosgiel, where you see all of the houses and the farmland, this is a really flat area, and this is what we call the Taieri Plains. On either side of the Taieri Plains, you see ranges. So on the right-hand side here, we have Maungatua, and on the left-hand side, just behind the trees, we've got the coastal ranges and Saddle Hill. So this is a valley where the Taieri Plains are, with two ranges on either side of that valley. The reason that the Taieri Plain is so flat is because it is a fluvial floodplain. So underneath all of the houses and the paddocks here are floodplain sediments. These are fairly young sediments from the Quaternary time period. Whereas the ranges on either side of this valley are composed of different rock types. So on the right hand side here, Maungatua, this is composed of the karst schist. So this is basement rock that has been uplifted a significant distance along a fault. And that fault is running right along the base of the Maungatuas. And you can see that there's a pretty sharp change between the flat topography of the Taieri Plains and the ridge itself, the Maungatuas. You'll also notice that Maungatua is sort of, as we look towards the west, so further right, it is dipping down a little bit. The horizon that we see there is sort of decreasing down towards the right hand side. That surface is an erosion surface. So remember back to the North Otago field trip where we saw a non-conformity between the karst schist and the overlying Taratu formation? This is the equivalent erosion surface non-conformity right here, but instead of seeing sedimentary units on top of it, all we see is schist right here. On the left-hand side, behind the trees here, the reason that we have higher topography over here is because there is another fault running along the base of the range, and also the coastal ranges and Saddle Hill are capped by Dunedin volcanics, and we know that volcanics like basalt, it's a rock type that's fairly resistant to erosion, so it acts as a resistant cap to the sedimentary rocks that are below it. All right, so here we are at stop 2 of the day. We're here at the Outram Ridge, and this is the bridge here behind me, and this is the Taieri River, and this is where the Taieri River comes out of the Taieri Gorge and flows out onto the Taieri Plain. So we are looking upstream right now, and this is sort of north-northeast direction. And behind the bridge here, you'll notice that there are some hills, and those hills is where the gorge cuts through. The hills are made up of schist, and this is actually where the Maungatua fault runs right here between where I'm standing and the hills behind us. So the river is coming out of the Taieri Gorge and hitting the plain right where we're standing here. You can sort of tell from looking in this direction that the Taieri River is relatively low today, and that it does get a little bit higher than this in times of flood. One clue that tells you that is that there's a really large tree which is caught at the base of the bridge just up here at quite far away from where the river is flowing today. The water is also running pretty clear today, so we can tell that it's not carrying any suspended sediment in it. What we're standing on right here is a bunch of gravels. So the great thing about rivers is that they're eroding as they move through the landscape. And so when we look at the sediments in a riverbed, this is a representative sample of all of the different rock types that occur in the catchment of the Taieri River, so further upstream. So should we take a look at what we've got here?
Sure, let's have a look.
So I can point out a few different rock types here. First of all, we have a pretty large clast right here of schist. This is the Haast schist, and we can tell that it's schist because we can see this really nice foliation cutting across the clast, and it's folded in some areas. And we can see lots of smaller pieces of schist in here as well. Another rock type that we have here is volcanics. So this here and this piece here are small basalt pebbles. It's really dark, fine-grained volcanic igneous rock. We also have some really brick red pebbles in here, which are pieces of chert. And then here we have a different rock again, greywacke. And we also have clasts that are pretty much 100% quartz as well. So where do these all come from? It's likely that a lot of the schist comes from just up in the Taieri Gorge right here. Remember, we have uplifted Haast schist basement occurring up here. The greywackes and the basalt and the chert, these are probably being sourced from the Kakanui Mountains. So this is the mountain range that sort of splits up the Dunedin area from North Otago, where we visited on the North Otago field trip. And the quartz is probably also sourced from the Haast schist as well, because we know that schist can be cut by pretty large quartz veins. So, in terms of the grain sizes that we have here, there's a pretty big mixture. We've pointed out some of the larger clasts here, but in between them, we've got a bunch of granules and maybe even coarse sand right here. Moving on to the next class size up, we're still in gravels, but now we're looking at pebbles. So pebbles are anything between 4 millimeters and 64 millimeters. So that's 6.4 centimeters. The final class size is cobbles. So this is where we're getting to greater than 64 millimeters or 6.4 centimeters in diameter. And this schist clast falls into that cobble category. Because we're going from everything from cobbles down into sands, we would call this a poorly sorted sediment. You'll notice that these clasts have a variety of clast shapes, so the roundness here is pretty variable as well. A lot of the schist is really angular, whereas a lot of the basalt, the chert and the greywacke is pretty well rounded. And remember that the clast shape and to some extent size loosely corresponds to how far these clasts have travelled downstream. So it's likely that this schist was sourced from relatively closer to where we are standing now compared to this greywacke, basalt and chert, which was probably sourced from further upstream in the catchment. You'll notice that the majority of the sediments here are actually schist. So if we counted how many clasts of every different rock type we had here, proportionally the schist would make up most of those clasts. So right now you can go ahead and fill in table 2 of your field trip handout with the information that we've discussed here.
One of the things we discussed in the lecture is this concept of discharge, which is cubic meters of water per second. And we can calculate Q here in the field if we have just 2 bits of information. What we need to know is the cross-sectional area of the river channel, which we would give to you in the lab. And then the other thing is we need to know the water velocity, so how fast the water is flowing here. Well, what we need to know is a certain distance, so a known distance, and we need to know the time that it takes for an object to travel from one end to the other. So one of the tools that we can use here is we need a current meter of some sort. This is our biodegradable current meter. I've taken the little plastic sticky label off, and so this thing's going to float away down the Taieri and biodegrade somewhere else. The other thing is we need a tape measure, and we've chosen a 50-meter tape measure. That's just lying over there. And now Sophie and I, we're going to set out our experiment here, and what we're going to do is we're going to chuck the orange in the water in the middle of the stream, so not at the sides, because we want to get a good average, and the average should be about the middle. It's not flowing terribly quickly today, so we're going to throw that in there, time how long it takes to get to the other end, and then we're going to calculate our velocity once we've done that exercise. Well, welcome to Allenton. So this is about 7 kilometres downstream from Outram, where we were before, and we've just driven along the countryside square across the Taieri Plains, roughly in the direction of Dunedin Airport. Behind me here is the Taieri River. It's changed its character a lot. The velocity you'll see is quite a bit slower. It's actually very tranquil today, and the water level is very low, much lower than what we're used to on this field trip. The main point in this stop here is to show you that the river's not the same as it was out at Outram. The water's moving a lot more slowly. The particle size is very, very different as well. So what we're going to focus on here is we're going to do the same thing at Outram. We're going to look at what the sediment particles here are. We're going to try and find the differences. We're going to try and characterize those particles. And then we're going to determine the river velocity. And we're going to do the same experiment as last time using our current meter, so our oranges, and a tape measure. In this river system here, we would have something called a point bar and a cut bank. So right now I'm standing on the point bar. This is the entire point bar, and the river carries on around the corner behind me. This whole thing would be called a point bar. On the other side of the bank here is our cut bank. And so what the river will tend to do over time, it'll migrate out, it'll keep cutting the bank, and it'll continue to deposit sediment on the inside of this point bar here. At Allenton, the sedimentary particles are much smaller than they are at Outram because the large particles fell out of suspension shortly after Outram when the river transitioned into a meandering river system. This meandering river system here is much better suited at moving water than it is moving sedimentary particles. Well, welcome to Old Henley Bridge. This is our fourth stop for today's field trip. We've just driven about 20 k's down the road, 15-20 k's down the road from the previous stop, past Dunedin Airport and across the Taieri Plains. It's the outflow of the Taieri River and also of the water of Lake Waihola. And the river here flows through an antecedent gorge. What that means is that the hills slowly grew, but at a rate that was slow enough that the Taieri could consistently cut through it. During flood events, it would slowly create a channel and carve a channel that gets deeper and deeper and deeper with time. So that is an antecedent gorge. The other thing that's important to talk about here is sea level. So right now, the water is flowing towards the ocean, so towards the gorge. If we were to come here at high tide though, and usually we try to time it like that, then you would see that the water actually flows the other way. So what do you think that tells you about this river? It's very, very, very close to sea level. So close to sea level that during high tides it reverses and flows the other way. It also tells you one thing about the Taieri Plains, and that the Taieri Plains are not very high above sea level either. Figure 2 in the handout, or the sea level curve, has some years on it, so time is written on there. And it also has a scale on the far left, which is your sea level itself. This is the change in sea level over the last few thousand years since the last ice age. So during the last ice age, sea level was a lot lower. Here it was about 140 meters lower. So you could have walked all the way along the coast, all the way basically to the continental shelf edge. That would have been the old coastline. Also the South and the North Island were connected by a land bridge, and Stewart Island was also connected to the South Island. So it was one big long island. New Zealand had no North or South Islands or Stewart Island. As sea level rose though at the end of the ice age, it eventually came up to where it is today. One interesting thing about that sea level rise, as you can see, is that there are some steps in the sea level rise. So that tells you one thing, that it did not rise evenly through time. The question we need to answer now on this handout at figure 2 is, when did sea level reach its modern level? Another quick thing to think about here when you're looking at this is, did sea level reach its present level and stay there? Was it higher sometime in the past? So the next bit is, what did the Taieri Plains look like when sea level was higher? If the Taieri Plains are already very close to sea level today, it's possible then that the Taieri Plains were not a flat, let's just say pastoral area with cows and things like that. The odds are that it was an estuary. So the other thing that we want to talk about today here at this stop, and that'll be Sophie's job, is the Henley Breccia. This is a special rock unit that's behind the camera here. And it is a very ancient rock unit that's been here for many, many more millions of years than the Taieri Plains itself. And the reason the breccia is there is because we're actually standing on a fault. This is an active fault. It's called the Tea Tree Fault. And it is the boundary between the coastal range and the Taieri Plains. On the other side of the Taieri Plains, at the base of the Mangatua Hills, we have the Mangatua Fault. So one critical thing about faults that you have to show is the fault motion. And so in this case here, the Taieri Plains, obviously it's the plain, it's the flat bit, and the hills are the up bit. So the up-thrown side is behind the camera, which is the coastal range, and the down-thrown side are the Taieri Plains.
Okay, so we've just popped up from the road, which is where we were filming before at Old Henley Bridge. And we've come up here onto this driveway to see an outcrop that you can see right here. It's not a great outcrop and it's slightly overgrown, but I'm going to talk you through what we're seeing right here. It's a clastic rock. We see that it's made up of clasts of a variety of sizes, going all the way from cobbles down to sand. So we've got a poorly sorted clastic sedimentary rock, and importantly, these clasts in here are angular, so they're not rounded. So if we think about what we know about classification of sedimentary rocks, if we have a significant number of clasts that are cobble-sized and it's poorly sorted, then we're looking at either a conglomerate or a breccia for this rock type here. Because the clasts are angular, then it means it must be a breccia. Another thing that you can notice if you look closely in this outcrop is that the clasts themselves are imbricated. The term imbricated means that all of the clasts are stacked in one direction. How does that happen? It happens during transport of the clasts. So if we have unidirectional flow of a river, for example, river gravels will get stacked in one direction, which indicates paleocurrent. The imbrication that we see in the clasts that are part of the Henley Breccia here indicates that the flow direction, the paleocurrent, was going from the west to the east. So this direction, generally. So where did these clasts come from? One of the paleo environments that we talked about back in lab 2 was an alluvial fan. This is probably what the paleo environment was for the formation of this breccia. We had a mountain up here in this direction somewhere, and there was clasts shedding off the mountain due to erosion in this direction from west to east. So if we had a mountain up here, what's happened to that mountain now? Why isn't it no longer here? The reason for that is the fault, the Taieri fault. So the Taieri fault actually used to be operating in the reverse direction to what it's operating now. We had this side moving up and this side moving down, and that meant that we had a nice mountain range that was shedding off lots of detritus to build this Henley Breccia.